from 10th to 14th June 2020, organized by Department of Mechanical Engineering, Sri Venkateswara College of Engineering, Sri Perumbudur, Chennai. The objective of this faculty development program by the webinar sessions is to explore the challenging attributes in mechanical behavior of new developed materials for supporting and meeting to various engineering applications. We hope the program will be very much useful for the faculty members, researchers, and will give you a very good platform for knowledge sharing and for future challenges involved. So the FTP has 5 technical webinar sessions organized with the leading academicians and industrial experts as a resource persons from 10th to 14th June, covering various topics related to mechanical behavior of new developed materials. We have around 550 participants registered for this FDP from various states of India and various regions of Tamil Nadu as well. On behalf of Department of Mechanical Engineering SPCE, I once again welcome you all for this FDP and request your full cooperation in making this event a memorable one and a success. Thank you.
Thank you, sir. Now I request Professor Badrinathan, Dean, Educational Development, Sri Venkateswara College of Engineering, to deliver his presidential address. Welcome, sir.
Thank you, Sindhamarai. First of all, I'd like to thank the organizers for giving me this opportunity. So again, I take this opportunity to welcome the resource persons. I feel pleasure in naming them individually. Professor S.Balasivanandha Prabu from Anna University, Dr. Senthil Velan from IIT Guwahati, Dr. Srinath Gajapati from Tech Break Consultants, Dr. Dhanshekaran, AGM Ashok Leyland, and Mr. Vinod Kumar, Senior Manager Ashok Leyland. So I thank all the resource persons for accepting to be part of this FDP. And I also take this opportunity to welcome all the participants who have registered and who are part of this webinar. So I won't take much time, maybe not, to be precise, not more than a minute. Going back to my college days in 1980s, where the subject metallurgy materials was considered as a boring, vague, dry subject. I only assume that even today, the subject as such has maintained the same status. But then coming to the practical applications, so long back, we have moved from the conventional materials and metals starting from steel to alloys and composites. So there has been a tremendous development in materials. So what is that advantage of that? See, one side, the designers, they break their head to come out with innovative ideas and innovative designs. But how much ever innovative the design is, at the end of the day, it has to be manufactured. And if there are going to be constraints in manufacturing or choosing the right material for the product, then the amount of effort that has been put for the design is going to be waste. So that is exactly where the developments in material science and materials is helping the industry in coming out with innovative products. And now we have a wide variety of materials, as I told you, starting from conventional materials and metals to composites and what else and what not. So this development has given flexibility, a lot of flexibility to the product developers. And of course, we have Dr. Dhanshekaran from the Product Development Center of Ashok Leyland. So you'll be able to emphasize more on that, how this developments in the materials has given flexibility for the product development team. So this is one aspect of this. The another aspect is the latest manufacturing technology, which technically we call it as additive manufacturing, and commercially it's called as 3D printing. So if you want to list out the applications of 3D printing, the list goes endless, wide applications. So that is possible only because of the availability of variety of materials that gives the flexibility in using that 3D printing technology to a wide variety of applications. So these two, I think, this will clearly tell us why a lot of research has to be put into material development, material characteristics study, and things like that. So this way, I really congratulate the organizing team for having arranged for such a FDP. And again, a mixture of both academicians, researchers, and industry people who at the end of the day are going to apply those things into practical products. So I'm really happy about it. And I'm once again thank the team, organizing team, for giving me this opportunity. I welcome each and everyone for this FDP, and I wish the FDP a grand success. Thank you.
Thank you, sir. Now I request Professor Ramesh, Dr. R. Ramesh, one of our coordinator, to welcome our speaker.
Yes, sir. Dr. Balasivanandha Prabu is currently Professor of Mechanical Engineering, Department of Mechanical Engineering, Anna University, Chennai. His area of research include composite materials, ultra-fine grained materials, nano-structured materials, and cutting tool materials. He has contributed 6 book chapters to Handbook of Nanotechnology and special volume for aluminum lithium alloys and severe plastic deformation. He has authored more than 160 papers in international journals and conferences. He has filed 3 patents in the field of cutting tool development, and he has published a book on superplasticity published by Springer Nature. He has successfully completed 2 sponsored projects, funded projects by Department of Science and Technology. I am very proud to introduce Professor Balasivanandha Prabu. Now I am handovering the session to the speaker.
Thank you, Professor Ramesh Babu.
Yes, sir.
Let me thank the Department of Mechanical Engineering, Sri Venkateshwara College of Engineering, for giving me this opportunity to deliver a talk in this FTP. And also, good evening to all the participants who are seeing this lecture on the webinar Zoom platform. And today, my talk would be on development of novel TiCN based CERMET with the improved mechanical properties. Professor Ramesh Babu, I'm now sharing my slides. Is it visible?
Yes, sir. Yes, sir. It is visible.
Okay, then I can go ahead.
Yes, sir.
Yeah, it's now moving.
Yes, sir. It is
Okay. Okay. Thank you.
Yeah.
Thank you very much. Now, as you all know that majority of the engineering components are produced in the form of a machined component, and more than 15% of components are manufactured by machining activities or metal cutting processes. Normally, 20 to 25% of cost involved in the machining will be taken away by the lubricants as well as cutting fluids. Therefore, the dry machining is mandatory for current scenario, where this cutting fluids also very dangerous for the human being, and also the cost involved is also very huge. Therefore, considering these situations, nowadays people are recommending dry machining operations for machining environment. And considering the development that has been taking place over the past several years in the field of materials engineering, we are producing advanced materials which are very difficult to machine. So for that, we need high performance cutting tool material. And if you consider this dry machining operations and also the machining, the challenge associated with the advanced materials, the development of new tool materials are mandatory nowadays. Therefore, we need to prepare really a new material which should have a higher mechanical property to machine the advanced material. Some material machining are really challenging because we need to have higher hardness material, higher tougher material to machine those advanced material. So here, as you all know that there are several materials which were developed in the recent past, which were employed successfully for machining applications. For example, if you take a high-speed steel, where there's carbon composition ranging from 0.6 to 1.5, along with you have chromium, molybdenum, vanadium, and cobalt addition, that will give you good toughness, but the hardness value is very, very poor. so which are recommended only for machining ductile materials, where the machining ability, that means the speed of machining is restricted to 30 meter per minute. It is really a low speed, but still we call this as a high speed steel. But the machining capability is still low speed, 30 meter per second, 30 meter per minute. And we have an improved version of this cutting tool which is called carbides. We take tungsten carbide, tantalum carbide, and niobium carbide, which are cemented by means of a binder cobalt. And this has good hardness over compared to high-speed steel, but the toughness is very poor. And to overcome this, the hardness point, so the coated carbides are nowadays employed. But again, while machining the steels and cast iron, these tools are facing a lot of problems, and the wear resistance is one of the challenge in the carbide cutting tool. Therefore, people move on to develop a higher, harder material. We should have ability to cut the stronger material, and also you should have a very high hardness value. So in that aspects, the CERMETS are the one material where which has been nowadays in the metal cutting industries, which has very good hardness value compared to carbides, but the toughness value is very poor. So because of this, we cannot employ this tool for interrupted cutting, especially machining and interrupted drilling operations, where for a turning fine finishing operations, we can recommend the CERMETS. So apart from that, we have a silicon nitride, cubic boron nitride, and also diamond, which are recommended only for fine finishing operation. For rough cutting, we are still in the need of developing newer cutting tools, especially based on the ceramics. Now the alumina Al2O3, aluminum oxide, is employed as a cutting tool material because it has good oxidation resistance and also chemical inertness, which has still high hardness value compared to even carbides and CERMETS. Therefore, pure alumina, also the alumina plus 30% of THC. In addition, they are making some sintered composite body, ceramic composite body, which can be employed as a cutting tool material. So now the problem that we have plenty of cutting tool material, starting from high-speed steel to diamond. The diamond is considered as a superior material. Our ultimate aim should be to have a hardness value close to CBN hardness value or diamond hardness value. At the same time, we have to also have a superior toughness value. But the problem with the CERMETS would be, which has improved hardness value, but the toughness is really a big worrying problem, because the toughness value is still 6 megapascal root meter value. Therefore, it is a higher challenging thing nowadays to recommend this CERMETS for rough machining operation, whereas this is still employed for fine machining operations. Therefore, there are a lot of scope for research activity to improve the property in terms of the hardness value, in terms of the toughness value in CERMETS. So the presentations I'm going to discuss about how to improve these properties in the CERMETS. Now, if you look at the properties which are essential for developing a cutting tool materials, majorly now you should have 5 properties which are very important. One is hardness, toughness, impact strength, wear resistance, and also thermal shock resistance. These are very important property in which the hardness and toughness are considered as a most important critical property. And this toughness, the impact strength, if the toughness is good, the impact strength would be also good. So here I have a comparison of high-speed steel, carbide, and also some of the ceramics and CBN diamond. The hardness value keep on increasing in the ladder from HSS to diamond. So you have a hardness improvement. The CERMET has a medium hardness compared to diamond. Whereas the toughness aspect, the diamond has a very poor toughness, and the toughness for high-speed steel is really high. And similarly, the impact strength, because the brittle material will have poor impact strength, and wear resistance will also be very high because the hardness value is higher. As a result, the wear resistance is also higher for ceramic, CERMETS, and CBN and diamond. And also you can employ these tools for higher speed applications. And thermal shock resistance is very poor. The ceramic as well as CERMET material has weak point. It cannot be able to withstand thermal shock as well as mechanical shock. So therefore, the toughness is the property which need to be improved to improve the thermal resistance as well as the impact resistance. Okay, and in terms of this machining capability, and we have a good machining capability for ceramics as well as CBN and diamond. If you look at the chart, the light to heavy cut can be possible with the ceramics and cemented carbides, CBN and diamond. And also the finish obtainable is very good for ceramics, most of the ceramics, and also diamond, it is excellent. And also the method of processing, which the cemented carbides depending on hot isostatic pressing, and or it is consolidation followed by sintering, whereas all other advanced tool material, example the CERMETS and cubic boron nitride and diamond, which are manufactured by this method. Therefore, now in this lecture, I am going to specifically dedicate to CERMETS. So what is CERMETS? It's an artificial word given to a combination of ceramic materials. That means you have a ceramic component which is binded by a metallic phase. And here, TiCN is a CERMETS, which is binded by a cobalt or nickel or molybdenum. This is a binder. Okay, and CERMET has several good features. One, high cutting speed at moderate chip section. When the chip section is very, very moderate, the force required to separate the chips will be very, very lesser. That means the frictional forces or the frictional heat developed at the over the chip tool over the chip. That means that the chip tool interface, the temperature generated because of the rubbing action of the chip would be very, very minimum. So the minimum the chip thickness, you have benefits. So high surface quality of the machined piece, you can able to get the improved surface roughness value, and also high wear resistance. The tool has a high wear resistance. As a result, the tool life of this CERMETS are really commendable, and high performance reliability, high edge strength. So one important aspect is the edge strength, that we say the rupture strength of the cutting edge. The rupture strength of the cutting edge is really good, should be good for the CERMETS, and we have high thermal conductivity. So compared to ceramics as well as the cemented carbide, we have a very good high thermal conductivity the CERMETS carries. As a result, moment you have a heat generation at the chip tool interface, the heat will be immediately taken away from the cutting zone. As a result, there is no diffusion mechanism triggered, or there is no abrasion mechanism triggered, or there won't be any oxidation mechanism will be triggered at this interfacial junction. That means interface I am representing chip tool interface, the area over which the chip is flowing. So the high thermal conductivity is another important property the CERMETS has. As a result, the tool life of the CERMETS would be really higher. And the ceramic composition, this is a CERMET, is a ceramic material, which is normally a euchaxed fine grains of ceramic in the roughly varies from 15 to 80% in the binder alloy. And normally, when you compare this titanium carbonitride CERMETS with this tungsten carbide cobalt, the tungsten carbide cobalt composition is basically a cemented carbides, which is represented as a hard material initially. Now we are giving a name cemented carbide, but it's all two families of hard material. TiCN based CERMETS are a hard material. Another branch is tungsten carbide based cemented carbide material. When compared to this tungsten carbide and cobalt cemented carbide material, and we have good hardness, the TiCN has good hardness, but the toughness value is very poor. Whereas this tungsten carbide has really the edge over this TiCN in terms of toughness value. And because of the superior hardness value, the TiCN has wider applications in the refractory parts of a turbine engine, jet engines, diesel engines, and other gasoline engines. And also it is used as a drills and excavating tools in oils and gas industries, and also used as a wire drawing dies, bearings, and surgical tool and coating. So you have really a good applications of this TiCN based material. And if you look at the microstructure of a typical CERMETS, the typical CERMETS will have a three part. One is the inner core, another one is outer core, another one is inner core, outer rim, and inner rim. So normally if you take a TiCN, which is supposing embedded by a binder material, the binder material could be a nickel, cobalt or molybdenum based material, and the TiCN is a core material. The TiCN will have a reaction with some other material which are added over there, and it will form an outer inner rim. The inner rim is basically a solid solution of TiCN, which will have a reaction with other materials by dissolution precipitation mechanism that will form inner rim. And then over that, we will have a metallic binder that will be outer rim. So the major three important constituents are very, very important, because this will control the hardness and toughness value of the CERMETS. So TiCN is a core material, and followed by we have a solid solutions of TiCN, and with other material will form a inner rim, which is a solid solution. So as you know from the mechanisms of strengthening, the solid solution is also one of the strengthening mechanism. So a inner rim of solid solution would be also formed, and the outer rim we have a binder, so that will bind the material. So here the skeleton is basically a metallic skeleton. The metallic skeleton is your binder, and in which you have a solution which is inner rim, and inside you have some hard material. So basically the TiCN is a core which is more harder material, and inner rim is a solid solution which will have both the toughness as well as hardness. But compared to TiCN, the toughness hardness value would be lower here. And then followed by you have a metallic material which is surrounding these spaces, which will have really a good toughness value. Therefore, depending on these three important parameters, the hardness and toughness value of this material would be changed. So you can able to tailor made this material by modifying the microstructure. One can able to modify the hardness as well as the toughness value. So we are going to play with this kind of a mechanism in the future. And also you can able to make a coreless structure. So sometimes the TiCN core won't be there when the particle dimension is very, very finer. For example, nano kind of a particle, if you, and this will have an immediate solid solution reaction with the other ceramic material. As a result, there won't be any core, but instead you will have an inner rim as well as outer rim, which will be forming. As a result, the problem with the coreless structure is you will have extremely good toughness value, but the hardness value would be poor compared to the conventional TiCN based material. So here, the recent past, there are so much of composition people proposed, because one can be able to modify the composition of the CERMET composition so that you can be able to get the hardness and toughness value to the standards of the hard material. So in the year 1930, the TiCN MO2C and NaMoCr based material, which were which is actually a CERMET, TiC based CERMET material, but at that time it was not represented in the name of CERMET. It was marketed in the name of titanate, because it is titanium carbide based material. And then during this 1949 to 55, TAC, NBC, NiCO, CR based composition was proposed, that people represented as a CERMET composition. So the first word CERMET composition was given to this composition. When later TU Vienna University, they have nitrided this TiCN based material, TiCN based composition. As it is, as you know, the nitriding is a one of the surface modification technique, where on nitriding you can be able to get an improved mechanical property at the surface. So on nitriding this TiN, there is a precipitate of TiN is also formed, which is something like a composite combination as a result of nitriding, which gives improved hardness value. Therefore, people understand from this point of time that nitriding the TiC, and also we can make a nitride solid solution of this N into TiC. As a result, you can be able to make a really wonderful material. Therefore, the TiCN based composition were proposed in the year 1974, and later on people modified this TiCN with other ceramic material also. So I have a list of composition here in the year 2009, and the TiCN and the Ni was compacted and sintered, and which was recommended for cutting tool industry. And then later in 2011, also people modified TiCN with the molybdenum, tungsten, and vanadium, where in the presence of a binder nickel and then cobalt, it is recommended as one of the cutting tool material. And there are several other compositions also proposed. Okay, you can able to modify with tungsten carbide and niobium carbide or tantalum carbide, and some other compositions also. So these are different compositions people recommended. Still then, the problem faced by this titanium carbonitrate based CERMETS are, it is really weakening, really suffering due to fracture toughness value. And the hardness point of view, it is showing some good improvement and adding this secondary carbides. But one thing you have to remember that the microstructural modification is necessary, that you have to control the core structures, you have to control the inner rim formation, outer rim formation, then you can be able to play with the modification of hardness and toughness value. Here, the addition of tantalum carbide and niobium carbide really improves the cutting performance in the interrupted cutting. So it can be a substitute in the titanium carbonate. So along with the titanium carbonitrate, you can also add tantalum carbide, niobium carbide, supposing if you are recommending this composition of the tool for milling application. So for an interrupted cutting, you can add this tantalum carbide, niobium carbide, and addition of tungsten carbide and molybdenum carbide, which is acting as a binder, therefore, which will improve the densification. So this diagram represents the effect of different secondary carbide additions on the CERMETS. So silicon carbide addition, it is a good grind refiner. The grind refiner, that doesn't mean that it is going to refine the starting material powder size. It will retain the starting material powder size. It won't allow the grain growth to happen. So it is a good grind refiner. It will be sitting in the boundaries of two TiCN particle, and it will stop the diffusions. And then you have a titanium nitrate, which can be also added to improve the wear resistance, because nitriding or nitride can improve the wear resistance and hardness. And also it is a grain growth stability material. Then Si3N4 can be added to improve the hardness value. And the hard hardness can be improved by tantalum carbide and niobium carbide. And specifically, if the tool wanted to, the tool has to have a corrosion resistant, then Cr3C2 can be added. And for improving the toughness, you can add cobalt, nickel, titanium, any metallic element which has to be a binder material. Then the toughness can be improved. Then you have a cubic boron nitrate, which can be added to improve the transverse rupture strength. Then obviously the tungsten carbide and molybdenum carbide, that is going to add the sinterability. That means it is going to improve the wettability of the titanium carbonitrate. And during the sintering operation, this helps to have a good sinterability. And wetting is a good wetting is an initial phenomena, required phenomena to improve the sinterability. So the compositions, CERMET compositions should also have this binders as well as this sintering aid material. And what is the percentage of addition that is recommended for every case? The tungsten carbide, you can able to add a tungsten carbide up to 50%, because it has solubility up to 50% in TiCN based CERMET. But the thing is, above 20% of addition, that doesn't have any good improvement in the mechanical properties like hardness and toughness. Okay, therefore you can go up to maximum 15 or 20%, where you have a remarkable improvement in the hardness and toughness value. But here the fracture toughness density increases with increasing tungsten content. So the increase, if you notice this increase, the increase is not really a substantial increase, but there is a slight increase in this value. But the hardness value would be really high. And also we can add a nano-based material. So nano-based, I mentioned that silicon nitride is a good harder material. For hardness improvement, you can add this material. But what is the effect of adding nano kind of a material over there? Supposing if you have a rim structure formation, you assume a TiCN and you have an inner ring formation. Supposing if you are adding a nano-sized material over there, okay, so this nano-sized material will be dispersed uniformly in the inner rim as well as in the outer rim. Outer rim is a metallic phase. So fine distribution of this nano precipitates or nanoparticle in the inner rim as well as in the outer rim, that will prevent the crack propagation. and also delay the crack propagation, and also it will deflect the crack propagation. As a result, the toughness value would be increased. So here the silicon nitride is not only going to improve the hardness value, but it is also going to improve the toughness value by uh, uniformly distributing themselves in the inner core as well as outer core. And here the relative density is also increased, and addition of the Si3 and 4. The relative density is basically maintained up to 1%, but there is a drastic reduction after 2%. So there would be some reduction due to this addition. And also because the nano particle will form agglomeration, as a result it would affect the sintering. But the thing is, you have to, when you add a nanoparticle, you should have a well uniform distribution of this Si3 and 4 or any other nanoparticle should be uniformly distributed in the powder compaction. So otherwise this density would be a problem. Then we have a hardness value. If you look at the hardness value, the addition of silicon carbide to an extent of 2%, that there is a tremendous improvement, even 2 times the improvement, the hardness value as well as the fracture toughness value. Above that, fracture toughness as well as the hardness value is coming down. The transverse rupture strength as well as hardness value is coming down. That means you can effectively add this nano-based material up to 2% here. Okay, and people nowadays, because where this nano is a basic stuff people take into account in their research activities. You can also add a nano starting powders, but the thing is, it should not be completely a nano composition of every element. So probably you can have a few elements which are secondary carbides can be a nano starting material, not the primary material as a nano material. Otherwise, no, you will end up with the coreless kind of a structures where the hardness won't be improved. Only, you will have improvement in the toughness value. Therefore, the nano starting powders can be recommended only for a secondary carbides which can be added there, and that will be uniformly distributed in the inner rim as well as the outer rim, but the core remain unaffected. So sometimes you can also include this material inside the core. That is a different issue. Okay, so here, what are all the properties that one can improve by adding this nano based material as a secondary carbide or secondary nitride or secondary borides? The hot hardness would be improved, and there would be a much oxidation resistance and high temperature grip resistance and wear resistance would be improved. Now here, specifically some of the alloying elements we used to add. The alloying element will be sometimes metallic element, or the metallic element in presence in the compound or in the starting material. So what is the role of this material? Carbon content, it is going to decrease the amount of titanium and molybdenum dissolved in the binder. And one important property that carbon is going to increase, the more carbon percentage in the TiCN or probably in the TiC or WC addition, that is going to increase the hardness and decrease the toughness. So this point has to be remembered. Then the molybdenum addition, it is going to assist the sinterability. That's probably it is going to improve the wettability. That means the toughness aspect it is going to increase. Then if you look at the carbon and nitrogen content, it is going to make a solid solution with the other metallic element. So the nitrogen and carbon, which will form solid solution with the nitrogen, nickel, cobalt, molybdenum, titanium, and tungsten, and it's going to control the grain size. And ratio of nitrogen to carbon plus nitrogen is also very important. In any case, if you take a different composition, in any case, the ratio of nitrogen to carbon plus nitrogen should not exceed a 0.5. So in that case, if it is exceeding 0.5, there will be a distortion in the cutting tool. And also the nitrogen concentration is stabilized in the core, but gradually decreases in the cell because it will have a reaction, as well as sometimes because of the prolonged sintering time, the nitrogen at the outer surface will be also vaporized. Okay, that nitrogen elimination would be there. So therefore, that is also another issue here. Then we have a tungsten carbide. This tungsten carbide is one of the element which will improve the wettability. Okay, and tungsten carbide, molybdenum carbide, these are the material which will improve the wettability. As a result, it will aid the sintering. Then you have a tantalum carbide and niobium carbide that will definitely increase the resistance against the plastic deformation. And initially, I have told this is a element that you have to add to use the tool for milling application because it has good thermal crack resistance. And titanium carbide, it is a good material for hardness improvement. And also vanadium carbide, it is going to increase the fatigue strength. And nickel plus cobalt, it is basically going to assist the binding activity. So all these elements are very, very important. And one can, if you understand the basic core rim structures, you can able to you can able to play with the microstructures and then modify the mechanical property. And the work that I'm going to present, the objectives we have formulated, it is to develop a new TiCN based CERMETS with adding different kind of a ceramic reinforcement. So our objective is to improve the hardness as well as toughness value, basically playing with this microstructural modification. And the three important material we have selected, the secondary material. One is titanium nitride, another one nano TAB2, titanium diborate. Another one is nano silicon nitride, but I am not going to present this nano silicon nitride here. Okay, but probably I will discuss something about titanium nitride and addition of nano TAB2. And also what is the effect of cobalt, because it will be forming outer layer. And what is the effect of cobalt on this composition? And studying basically the microstructure formation and hardness, fracture toughness, and the porosity levels. And finally, the thermal stability, because if you want to recommend a cutting tool, the cutting tool has to be thermally stable up to high temperature. And also it should be a wear resistance material. And also you to suggest a combination of composition, better composition for a cutting tool applications. Okay, so in that aspect, now we have proposed nearly 6 compositions. In the first composition, it is represented as TN. So the TN represent, we have added titanium nitride. So to represent this titanium nitride, we are representing TN05. That means 5%, 10%, 15%. So the other compositions are same. So here TiCN is taken and cobalt is a binder material, and tungsten carbide that will assist the sinterability, and Cr3C2 that will improve the hardness value, and titanium nitride, this will improve the hardness value. So what is this effect of this titanium bearing titanium nitride in the hardness and toughness value? And other composition where nano TAB2 is taken. Now when you mix a nano titanium titanium diborate, and it will be uniformly distributed in the inner core as well, inner rim as well as outer rim. So as a result, what would be the effect in the toughness value and hardness value? Then for comparison of this thing, we have also modified, have a composition which includes the titanium nitride and a nano titanium borate, 5-5 composition. So that is taken. And TNB00, that is represented as a material for our comparison, because no other addition is added here. So the TiCN, cobalt, and Cr3C2 and WC, these are represented as a standard material, where based on which we will compare other composition in terms of hardness and toughness. And also we here the WC is modified. We keep nano TAB2 constant and Cr3C2 constant. And what is the effect of tungsten carbide addition in this TiCN? That is represented here. So this composition we are going to fabricate. And then another case where the cobalt concentration is changed, where keeping this nano titanium diborate and Cr3C2 composition and WC concentration common, and cobalt concentration is varying. And now I proposed five table in which we have several compositions, and initially the powders will be taken in a required quantity and it will be ball milled. So that means the number of experiments that we have conducted is really huge. For each case, we have prepared separately the powder composition and we have sintered the material. Then the experimentations includes the measurement of mechanical property as well as thermal stability, mechanical wear resistance, everything. So the initially, in order to mix these powders completely or uniformly, homogeneously, the ball milling was used, and WC cobalt tungsten carbide based balls were employed, and ball to powder ratio was maintained at 10:1, and we have milled this composition for 24 hours. That means every composition was milled for 24 hours, and during this milling, for every half an hour, acetone was added, because no other the heat should not produce no other composition or no other compound. So in order to have the control over the heat generation, we have also added acetone. Once the ball milling was over, we have heated. It's called annealing. So to relieve the thermal stresses induced during the milling, we are annealed this with the hot air oven for 2 hours at 110 degrees centigrade. And there are some problems during TiCN. It's a common problem for ceramics as well as CERMETS. The CERMETS are produced by powder metallurgy techniques. That powder metallurgy technique means you have to have a powders, and the powder has to be milled, or powder has to be consolidated and then followed by compaction, or sometimes it will be hot isostatically pressed. When it is subjected to hot isostatic pressing or the sintering cycle, it is a high temperature cycle where the specimens will be kept for long durations. Okay, so during this long duration, sometimes there would be a evaporation of removal of nitrogen. That's a one problem with the conventional powder metallurgy route, the CACN, where the nitrogen will be partially evaporated. And also, since it's going to be kept in the high temperature for longer duration, and there would be a obvious grain growth. So coarse grain tend to form during the sintering. So the TiCN try to diffuse with other particle and then try to make a bigger grain. So that is a problem where it will affect the mechanical properties and hardness, toughness, and rupture strength. And also the limitation is very poor fracture toughness, low fracture toughness value because of the sintering. And also there will be a differential densification. At the outer side, the densification would be better, and the inner core side, the densification will be very, very poor. That means it is something like non-sintered centric, as well as at the outer side you will have a completely sintered component. So that densification won't be uniform in the case of a conventional material. Therefore, here we have used spark plasma sintering, where the material will be loaded in the graphite die, and you can apply the pulsed DC current and also a pressure, okay, 50 MPa pressure and also pulsed DC. And because of this plasma heating of the surface of the power particle, okay, and there will be a heat generation, and also Joule heating because of the pulsed DC current, and also a plastic deformation because of the pressure application, and also heat that will create more densified components here. And also you can because this process will be quickly finished, and there won't be much of grain growth possibility here. Therefore, whatever the problem you have with the conventional sintering technique, like the differential densification, then you have nitrogen evaporation, as well as the poor the grain growth, everything will be stopped here. And the heating rate would be really 1000 degree Kelvin per minute. Therefore, heating can be done at the faster rate, as well as cooling can be also done at the faster rate. The advantage of this spark plasma sintering, where full density can be achieved, okay, now close to full densification you can achieve, and also the materials will be exposed to shorter time, as a result preventing grain growth, and also no obvious densification gradient. So everywhere the density would be the same at the outer surface as well as the inner surface, the density would be same. And here it is representing with respect to pressureless sintering, the SPS, the grain size is retained. Even there would be some grain growth, but the grain growth is not tremendous grain growth, okay, that can be easily controlled. And these are the process parameters we have recommended, and for sintering the CERMETS, 1500 degrees centigrade, and heating rate is 100 degrees centigrade per minute, and pressure 50 MPa, sintering time 15 minutes, and load 8 kilonewton. It is proportional to 50 MPa load. Now here, these variables were taken from the earlier studies conducted by different authors. Okay. Now here, if you look at the oxide formation, probably supposing if you take a powders, and the powder may carry some oxygen. So during the initial period of heating, there would be carbon monoxide emission. So that would happen during the real conventional sintering method. So when the temperature is increased, there would be also carbon monoxide emission, but this carbon monoxide emission would be very, very poor at high temperature. Similarly, the nitrogen emission also release will be also very high, up to 1300 degrees centigrade, followed by there won't be any nitrogen release, because other mechanism will be dominating. Once you have more than 1200 degrees centigrade, the solid diffusion, solid state diffusion begins. As a result, the nitrogen release will be removed, and also, and you have a dissolution, and dissolution precipitates mechanism will be also triggered at high temperature. Therefore, the carbon monoxide emission as well as nitrogen emission will be stopped. Therefore, if we take a temperature which is close to 1400 degrees centigrade and 1500 degrees centigrade, this would be a temperature where there is no nitrogen emission, nitrogen removal, as well as carbon monoxide removal, and also you will get a full densification. The sinter stringage is 100%. That means it is full densification. You can able to achieve close to theoretical density. Therefore, looking at this aspects, we have proposed this value. And also, after fabricating the CERMETS by spark plasma sintering, we can measure the hardness value by Vickers hardness tester. And also, the toughness can be measured by this Shetty formula. The toughness, it's a really challenging measurement in the ceramics. In conventional metal and alloy, we can take the stress strain curve, the area under the stress strain curve, which is equivalent to the fracture toughness of the material, because it is the energy absorbed before the fracture or the energy to create a fracture. So that means how much amount of energy is required to create a fracture. So that is a value that we take from the stress strain curve. But here, the crack propagation is depending on the stress intensity in the ceramics as well as in the CERMETS. Stress intensity. Therefore, one cannot take a simple stress strain curve and then area under the stress strain curve is equivalent to the fracture toughness value. It is something like a non-approved procedure. Therefore, there is a procedure which is proposed by Shetty, and where you can able to measure the fracture toughness from the crack emanated from the indentation surface. So that is a methodology that we have employed here. And the starting powder sizes and the microstructures are represented here. Microstructure, some micrographs of particle, and where the dimension can be also measured by the particle size analyzer, where the TiCN has 0.5 micron, okay, and WC has 0.5 micron, close to 0.5. Cobalt has really 3 micron, because you have to have a outer ring really little bigger. So in order to improve your fracture toughness value, and CR3C2 2 micron, and we here the nano sized TiB2 where it is 370 nanometers. So probably it can uniformly disperse in the cobalt matrix, as well as if the rim is formed, the titanium inner rim, titanium carbonitride, if it reacts with other material, ceramics, then the rim will also have this nano TiB2. So that is the ultimate aim of this work. Now, the powders after every composition after the milling, which we have taken this XRD to identify any other new phases are formed, to verify whether the phases are retained as if like a original phase, or do we have any other new phase formation. Luckily, we don't have any other new phase formation. Therefore, milling was purely employed for uniform mixing of powders. Okay, therefore, the uniform mixing was achieved, and also there is a little particle size reduction. That is obvious in the case of a ball milling, but no other the phases were formed. These phases are original phases that we have added with the composition. So these are the for the composition here, where the Y is a variable, titanium nitride is a variable, and the second case where the titanium diboride, nano titanium diboride is a variable, and the third case where we are varying titanium nitride and titanium diboride equally, and in the final case where we are going to make a tungsten carbide variable, and finally here the cobalt is a variable. So 5 variations, 5 composition, and some variations we have, and then these compositions are sintered by spark plasma sintering. Then after sintering, and we have taken a XRD, really it is giving some nice insights about the sintering, because the TiN, where there is a formation of CO3 and C, and the CO3C, the carbon which are coming out sometimes from the TiCN, okay, and which will react with the CO, which forms some kind of a CO3C based phases, okay, and also there are some few in few places we have seen the gray carbon graphite, okay, and also in the case of this TiB2, it is very really interesting. If you look at the some phases where very interesting phases are formed. One is the CR3, CR 0.5, W 0.2, and B. That means the CR2, CR3C2 and TAB2 has some kind of a dissolution mechanism or some kind of a solid solution mechanism by which this kind of a new phases were formed. And exactly at 5-8% of TAB2, there are two new phases which are very probably you can able to see at the curve B, where this 0, 3, 1, two peaks are merging each other. That means the phases which are identical to each other and the lattice parameters are identical to each other. As a result, it is merging in the single peak. So in order to differentiate whether this is two phases or one phase, and we have also taken same image where we can able to identify from the dark the bright field and dark field images, where we can able to see the one phase is basically TiCN, and surrounded by you have CR 0.8 and W 0.23 and B4 phase. This is a new phase which are formed by the reaction between CR3C2 and TAB2. Like that, now there are several phases, new phases formed, especially BN 0.26 and C 0.6. These are the different phases, okay, which are formed by the dissolution precipitation mechanism at high temperature. So sometimes it reacts with the TiCN and TiCN and TAB2, where this Ti4N3B2 is formed. And so like that, several compositions, several ceramic phases react and then form different interesting phases which are responsible for improving the hardness of this material. Like that, when you take, when you change the simultaneously the titanium nitride and titanium boride, we also have an interesting phase formation, and CR 0.8, W 0.23 and B4 phase, and one more new phase, CR5, TA4 and W. These are new phases because of the dissolution precipitation mechanism it is going to form. And similarly, in other composition, if you're varying this tungsten carbide also, there are different phases, new phases also formed during sintering. So now we can able to see the macroscopic property and what is the role of this new phases formed, okay, during the sintering. So this is a microstructure of a CERMETS after sintering, where one can able to see the gray rim structures and black core rim. So this, if you look at this, there is a black core and also there is a gray rim, and you cannot be able to distinguish the inner ring as well as outer ring, but it's a one ring. But if you go with the higher magnification, probably you can be able to see the inner ring as well as outer ring. Now, as of now, you can be able to see only the gray rim, which is comprised of both. Okay, and what is the effect of this varying TiN addition here? The porosity level, it is increasing. That means more the TiN, and during sintering there is a more removal of nitrogen from this source. As a result, wherever the nitrogen is removed, even in the vacuum conditions, the nitrogen is removed. There's close that places, still it's acting as a pores or pits or something, and the porosity is really increasing here. That is a bothering. Sometimes the networked porosity is also good in improving the toughness, but the porosity should not too much, but it should be limited porosity with homogeneous distribution. As a result, probably you will have a good improvement in the toughness value. Now here, the other cases is TAB2. Variation in the TAB2, one can able to see the densification. See, TAB2 addition improves the densification, and also porosity is minimized, and no other carbon separation is taking place, because whatever the carbon separates, probably it will give some other phases. Okay, a rim is formed around these sites, forming white coreless grains. So white core, gray rim. Sometimes you can have black core, gray rim. Here white core, gray rim. And the white core, gray rim is formed because of the precipitation mechanisms. Okay, precipitation dissolution mechanism. The gray rim is also a precipitation mechanism, and also along with the binder material, it would be formed. And one can be able to understand how much densification is possible with the nano TAB2 addition. Here the nano TAB2 is added, and without TAB2 there is a porosity and other thing that is available in the image A. Whereas increasing the TAB2 content, one can be able to achieve really a good microstructures. And also by changing this tungsten carbide, really you can be able to see the white core and gray rim structures. And also the benefit is increasing this tungsten carbide is also helping to reduce the porosity here. Okay, so that is another, because the tungsten carbide or probably the MO2C which are basically assist the sintering process. That means it is improving the wettability. As a result, it will remove the porosity, decrease the porosity. And another case where you have cobalt, it's giving a really wonderful microstructure. Look at this. Comparing to other microstructure here, for probably 15% of cobalt or 10% cobalt or even 5% cobalt addition, where there is full densification, there is no porosity here. And also you can able to see gray rim and the majorly, no, it is a white rim. That means it's outer cover. And gray core. Gray core is basically TiCN based particle. So here the porosity level decreases with the carbon CO addition, but here it is probably a data error in the CO10. Probably we have taken some microscope where the porosity is there. If you take other area, probably it would be. So, but here the general trend goes like this. There is a decrease in porosity level with increase in addition of cobalt value. Now, if you look at the hardness value, with increase in TiN addition, what is the effect? And now TiB00 is taken as your the material for comparison, because no other the secondary carbides are added here, which has TiCN and cobalt and also Cr3C2 and tungsten carbide, and the titanium nitride or titanium diboride is not added there. So the CERMET T is TN05. That means 5% of titanium nitride addition improves the hardness value 37%. That means one can be able to achieve the hardness value close to probably 17.5 something GPa in terms of GPa. And also predominantly the solid solution of CO3C was found in the microstructure. And further addition above 5%, there is insignificant. That means the effective, you can add up to 5% TiN. Above that, it is insignificant to improve the hardness value. And the TiB2 addition, the second bar chart shows the TiB2 addition. And it shows really a good improvement. Even for 5% TiB2, nano TiB2 addition, because of this formation of these spaces in the microstructure, the value goes to 19.1 GPa value. And after that, even if you add 10%, 15%, the value is constant. It is really fluctuating with the 18.5 and then 19.1 within that range. That means it doesn't have any other the significant effect after 5% addition. That means a 5% addition of this TiB2, nano TiB2, it's improved the hardness value tremendously. And also the tungsten carbide addition. So the tungsten carbide addition is basically improves the sinterability, and also it improves the hardness value. It is close to 20 GPa. It's nearing that value. So 15 to 52% of improvement. And also some other new phases were also formed. That is the responsible phases for hardness improvement. And also in the cobalt addition, when you have a cobalt ranging from 5 to 10, but it is here, if you look at this value without cobalt addition, but you have other elements like TiB2, TiN, but the cobalt is missing in the COZ00, where it is giving more than 20 GPa value. But among all the tool composition we have developed, without cobalt addition giving a good hardness value, but the toughness is really a problem. But we have to have a combination of good hardness as well as toughness. Therefore, we cannot recommend this as combination as a tool material, whereas we can recommend other composition as a tool material. If you look at CO15, you have really nice value, 19 GPa value obtained. So we have seen here what is the role of every addition. The TiN is improving the hardness value. Nano TiB2 is also improving the hardness value. WC is also improving the hardness value. And even in fact, cobalt addition is also not improving the hardness value much, because if you compare with the CO00, the hardness value is reduced. That means here the fracture toughness value is poor, but for addition of cobalt, the fracture toughness value is improved. That is the thing that we can understand from this curve. But I am going to provide you the fracture toughness value also for other tools. And the fracture toughness value that we have calculated from the Shetty's equation, where the Shetty's equation, the K1C is equivalent to 0.0889. HB is a hardness value in Vickers scale. That hardness value we know. And L is the load applied. And A is the crack length. What is the crack length here? on indenting the CERMET surface, and there will be a crack emanating from the edges of this indentation. If you look at this first image, there is a cracks emanating from the edge of the indentation. We can measure this crack length. If the crack length is really bigger, that means the load is propagating the crack without any disturbance. But if the crack length is lower, that means there are some barrier to crack propagation. So lower the crack length would be more beneficial for improving the toughness value. And also one can be able to see different mechanisms here. See, there are two mechanisms normally in the metallic system as well as ceramic system. One is called intrinsic toughening mechanism. That is normally the responsible mechanism for metals and alloy, where the defect generation, defect blocking, so microvoid generation, microvoid coalescence, and stopping this by means of precipitation. These are the intrinsic mechanism. That means by modifying grain size and the precipitate, so one can improve the toughening mechanism. The extrinsic mechanism, that means it is by creating more boundary. That means you are deflecting the crack. As a result, you are creating new surfaces. So the energy will be spent for creating the new surfaces, and also the driving force will be reduced because of this. And also when you have more amount of barriers like a particle, and the new surfaces will be also created. So that is a crack bending. And here the example is given. When you have a coarse grain, the path taken by the crack is very minimum. But when you have a fine grain distribution, the path taken by the crack propagation would be greater. That means more amount of energy is needed to propagate the crack to reach the failure. So the energy requirement will be greater. So that when the energy requirement is greater, the toughness value would be higher. So that is the case here. One can be able to witness several mechanisms in the microstructure. That is, a crack bridging is also there. Crack deflection is also there. You can able to see the crack deflection as well as crack bridging in the image C, as well as some fracture, transgranular fracture, intergranular fracture. If you want to split the particle, you need more amount of energy. That means the crack will be propagating across the particle. And if the boundaries are strongly binded, then to separate the boundary, you need a more amount of energy. That means these are the mechanism, extrinsic mechanism, by which you can improve the fracture toughness value. So we have measured this length, and substituting the length, and also the load at which the hardness value is taken, and also the hardness value, one can able to measure the fracture toughness value. The fracture toughness value for the standard tool that we have considered is only 5.5 MPa root meter. Normally for TiCN, as a individual TiCN, if you sinter, the maximum toughness value would be 6 megapascal root meter. That's all. Okay, it's a poor fracture toughness value. Now here, by adding titanium nitride, the fracture toughness value is really increasing. Okay, and it is even a common, the constant, because there is no improvement beyond 5% addition. And if you look at this fracture toughness value for the varying TAP2 addition, really you have a good value here, more than 7 7 megapascal root meter. And in terms of varying tungsten carbide, it is sometimes giving close to 8 megapascal root meter. And in case of the cobalt value, it is giving really more than 8 value. So for example, cobalt 15% addition with this composition, TiCN, tungsten carbide, and chromium carbide, titanium diporide, where you have this. So by looking at this hardness value as well as toughness value, okay, so now considering this, we have come to a conclusion that TiCN 15 cobalt, 15 tungsten carbide, 5 Cr3C2, 5 TAP2 show the highest hardness fracture toughness value. And also the hardness value of this composition is also close to 19.1 GPa. Therefore, this can be recommended for cutting tool application, where the fracture toughness value is also 8.4 megapascal root meter. But another challenging question is, this is only satisfying the static mechanical property like the hardness and fracture toughness. Now we have to know the thermal stability. What is the response of this composition at high temperature environment? And also, what is the response of this composition on the wear environment? If those two conditions are satisfied, probably this can be employed as a proper cutting tool material in the cutting tool industry. Now, if we are carrying out the thermal stability study, as well as for wear studies, we have prepared the samples from this, and the sample represented here are representing the pin for wear testing, and another one for thermal stability annealing studies. Okay, that are wire cut EDM. By wire cut EDM, we have done it. So now here, what is thermal stability? It's the stability of a material or any material. Uh, uh, the mechanical properties has, what is the temperature range with which the mechanical properties are stable, or what is the temperature range with which I can able to use the material for effective operation. That means one can able to assess the thermal stability of every material by 4 means. That means you can measure the hardness before annealing, after annealing. Basically, you have to perform annealing study. That means the different specified temperature for a specified duration, the material will be subjected to this temperature and duration. Okay, after then it has to be cooled in a controlled manner. That means it is a furnace cooled. It is not a rapid cooling. That is an annealing operation. So it will be subjected to a 600 degrees centigrade 4 hours. Once that 4 hours is over, then the furnace will be allowed to cool on its own rate of cooling. Okay. So like that, now we have taken a different temperature and constant choking time. And after annealing, we can be able to see what is the variation in the hardness value, what is the variation or any other mass gain is there or mass loss is there in the material, or any other new phases are formed due to this temperature exposure, or probably we can also measure the grain size. What is the grain size before annealing, after annealing, if there is any grain growth possibility is there. So one can be able to say what is the temperature domain with which the mechanical properties are stable. Therefore, that is the temperature range which is recommended for the operation. So beyond that, if you work on the material, probably you may lead to some catastrophic failure due to various phenomena like new phase formation, or probably grain coarsening or something like that. So we have conducted this thermal stability studies for these 3 temperature, keeping this constant soaking time. And if you look at, for this, we have taken only TiB2 and TiN based composition, because we have now, and keeping this cobalt constant. Therefore, if you look at this curve, and this Sang et al. Sang in the year 1993, he has come out with the value for this thermal stability. TiCN based material has the micro hardness value 5.9 gigapascal after heating 1000 degrees centigrade. So this is the value, but earlier without heating it might be 12 GPa, but after heating to 1000 degrees centigrade, the TiCN based CERMETS showing only for 5.9 GPa hardness value. TiC based CERMETS are offering only 4.9 value. Okay, now for our composition, if you look at the hardness value after 1000 hours of heating, after heating to 4 hours at 1000 degrees centigrade, the value of hardness value close to 7 GPa. Okay, so even at 800 degrees centigrade, the value is close to 15 GPa. So the first curve, which has the TiB2 content, which is really a good CERMET composition, which is superior than the available literature value. Okay, so this is a one which is showing good improvement. And another mass gain, the mass gain. So mass gain is proportional to the oxide formation. So when you expose to in a controlled environment, normally when the tool material will be engaged in the ambient atmospheric conditions where oxygen is there at high temperature, the oxygen can react with your tool material or work material, it can be easily oxidized. Therefore, the oxidized based wear mechanism is also one of the responsible mechanism for wear in the cutting tool. Therefore, here the mass gain we are measuring. And here also, if you look at the bottom curve, which is the TiB2, 5% TiB2 based CERMET, where up to 800 degrees centigrade, it's showing least mass gain. That means up to 800 degrees centigrade, the stability is really commanding. But for all other tool, the 1000 degrees centigrade, there is a mass gain. That means there is a oxidation, tremendous oxidation formation. And one can be able to see the grain growth also at a different temperature of heating. If you see the 600 degrees centigrade TiCN, where there is no much grain growth, but you can be able to witness lot of grain growth in the specimen heated to 1000 degrees centigrade. Okay, so this would happen in the 5 TiB2 also. For the I have minimized the number of slides here, and here I have taken 5, 10, 15 TiB2. But all these conditions, the microstructures look like this. There will be obvious grain growth here. And also one can be able to see a lot of oxide formation. So now there is a tremendous oxide formation at the 1000 degrees centigrade. Look at TiO2, TiC, CrO4, Cr2, chromium is transforming into chromium oxide, then chromium O3. So more compound oxide phased material phases are were formed after 800 degrees centigrade. Up to 800 degrees centigrade, the formation of oxide was also there, but the formation is very limited. But at 1000 degrees centigrade, the formation is really, all these elements were converted into oxides. Really like that for the titanium nitride variation in the composition was also subjected to annealing cycle, where the sintering shows the grain growth at 1000 degrees centigrade, and also a lot of oxide formation at 1000 degrees centigrade. Okay, so this gives that the tool that we have proposed is stable up to 800 degrees centigrade. Probably if I conduct another experiment at 900 degrees centigrade, probably I can give you a very close value of thermal stability, but we have not conducted this 900 degrees centigrade. It's on process. Therefore, because it's a lot of trial that we have to do, therefore we have limited the number of experiments. Now again, another experiment is a wear studies. Now we have taken this pin CERMETS as a pin material, and we have used EN31 steel as a disc material, and we have conducted the wear testing wear testing, and the wear test shows the TiB2 as well as 5% TiN based modified tool as well as TiB2 modified tool shows. You look at this value at 0.47 and 0.35 meter per second velocity conditions. The wear rate is very, very lower. That means these cutting tools are really worth to employ at high speed cutting conditions. So the wear is very, very low when compared to other conditions. And also one more benefit is coefficient of friction. The coefficient of friction is really keep on decreasing with respect to high speed. So because the coefficient of friction, when the coefficient of friction is reduced, the frictional forces will be reduced, and proportionately the heat generation generated because of the friction will be also reduced. As a result, the chip tool interfacial heat will be reduced. That means the tool life will be improved, and it also has an effect on cutting forces. As a result, you have to have a minimum coefficient of friction. So at high speed cutting condition, the coefficient of friction is very, very low for the developed tool. So from that, I can be able to say that by modifying core rim structures, one can be able to even play with the microstructure modification, and you can be able to change the hardness and toughness value. And here the new phases which are formed by the addition of TiB2 and TiN, which are responsible for improving hardness as well as the toughness value. And the CERMET with this composition, nano TiB2, 5% nano TiB2, has a balanced improvement in the hardness value, 19.1 GPa hardness, and toughness 8.4 megapascal root meter. And also we have employed cutting metal cutting operations also, but those data I have not presented because it's really a metal cutting kind of a work. Therefore, this is employing this. It's a nice combination of composition which is recommended for cutting tool applications. So that is our conclusion from this study. The majority of this findings were published in our the papers in the top international journals, Ceramic International and the Journal of Refractory Metals and Hard Materials. And all our results are available here. And if supposing the viewers are really interested, you can be able to download these papers from the sciencedirect.com and also verify the results here. Thank you. If any questions are there, I can be able to answer the question. Thank you.
Yes, sir. Thank you, sir. Any questions from participant side? Dr. Sandhamarakannan, sir.
Yes, sir. Still, we not received any question in the chat box, sir.
Yes,
Still we
sir.
not received, sir. Still we not
Okay.
received any question from the chat box.
Yes, sir. I have one interesting question, sir, regarding the CERMET. I observed that 15% of with the titanium diboride, it is giving very low wear resistance.
Yeah.
So it is a very nice, interesting observation.
Yes.
So how and what makes this tremendous reduction in the wear resistance? How it is very nice, sir. It's a good result.
Yeah, the TAB2, the hardness value of TAB2 is really higher. It is more than 20 GPa hardness. And
Okay.
also the high temperature, it is one of the high temperature material. Their melting temperature is more than 3000 degrees centigrade.
Yes, sir.
And also we have added nano TAB2. That means
Okay.
this nano TAB2 will be distributed in the inner rim as well as the outer rim. As
Yes,
a result, since it is very, very harder and because of the wettability nature of other constituent, that is tungsten, it is very binded uniformly with the tungsten carbide core material. So separation would be the problem, because and also you have several phases which are formed next to TAB2, which will have a good bonding effect. As a result, the wear resistance would be very, very excellent.
Oh, nice, sir. And is there any scope for formation of build-up edge formation? I mean, that is build-up edge formation with
So
the CERMETS.
actually, the interesting from our machining studies, we have noticed there is no built-up edge formation. There is no what is called a fracture of edges. It is only the abrasive wear which is dominant. Other wear mechanisms are absent, like oxidative wear, fatigue wear, as well as sometimes we used to get a break up the edge also. So that breakage is also absent here.
Yes, sir. Any questions, Dr. Santamare? Still most welcome. If any participant interested, you can.
Sir, there is a question from Dr. M. Gajendran.
Yes, sir.
How to correlate hardness in gigapascal with Rockwell?
Yeah, there is a chart available. And also there is a formula available to convert this hardness, whatever hardness you have to convert into gigapascal.
Yes, sir.
Okay, so if he needs some formula, probably he can send a message to my email ID. I can give the proper reply as well as supporting material.
Thank you, sir.
Okay.
If no more question, I request Dr. Gopinath, one of the coordinator of this event, to give thanks to the speaker.
Good evening, one and all present here. On behalf of Department of Mechanical Engineering, Sri Venkateswara College of Engineering, I thank Dr. S.Balasivanandha Prabu, Professor, Department of Mechanical Engineering, College of Engineering, Guindy, Anna University, for the valuable presence and informative lecture. Thank you very much, sir.
Thank you.
I thank all participants for the patient listening. I thank our management, principal, HOD for permitting us to conduct 5-day faculty development program. Once again, I thank one and all present and attending the webinar. Thank you, sir.
Yes, sir. Thank you, sir. Tomorrow, the title for the webinar section is Design Challenges in Thermoplastic Composite Mission Elements. The talk will be given by Dr. Sendil Velan, Professor, Department of Mechanical Engineering, Indian Institute of Technology, Guwahati. So I request all the participants to join for the session on time. And also, the link is provided in the chat box. And I request all the participants to fill the feedback and attendance form, and accordingly we can wait for a few more minutes definitely till you complete your task possible. Yes, sir. Thank you all.
Sir.
Sir, இப்போ சார் போயிட்டாங்க, பாலசிவானந்த பிரபு சார் போயிட்டாங்க சார்.
Yes, sir. Sorry. Yes, sir.
We will end the live recording, sir. Live recording we will end, sir. Live stream.
Okay, there may be some people can get the link from chat box and on live session, no?
Separately we are posting it, sir. Separately we are
fine.
posting in the YouTube, sir.
Oh, then it's fine. Okay, then it can be stopped.